Quantum physics sits in stark contrast to the classical physics we've been studying this year. All year we've believed that there are physical reasons for the way things behave, that there are these mechanisms, that laws of physics governing how things are going to behave, that it is, if you know the initial conditions, then you will know what's going to come next, and that if you can figure out how all the parts, if you break something into parts and figure out how all of them work, you can put it back together to figure out how the whole will function. Whereas in quantum physics, we find that there is not this independent mechanism that is governing how things work, that in fact our observing and how we choose to observe affects the nature of reality, that you cannot start with initial conditions and know what the final conditions will be. We can only give probabilities for what will happen, and in fact our understanding is that all of those are happening before we figure out what the final is, and that you cannot separate things into parts, that they remain connected. We say they remain quantum entangled. So how did we get here? Well, at the turn of the 20th century, a lot of physicists thought that we had figured out physics. Maxwell did not, but with his work, people thought, hey, we figured it all out. One of the few details left to resolve was something called the ultraviolet catastrophe. And in working out a solution to this phenomenon, quantum physics was born, and with relativity and quantum, which both happened in the first decade of the 20th century, physics got turned on its head. So, the ultraviolet catastrophe. Let us start with the fact that as you make things hotter, they give off more and more radiant energy, and the color they give off changes. The first radiant that you hear is red, then it goes to yellow, then it goes to white, and in fact it goes to blue if you make it even hotter. That they had figured this out. They had figured out exactly how much radiation was given off at these various temperatures, and they had also figured out the peak of these black body radiation curves, that it starts off sort of in the the infrared, giving off radiant heat, and then it moves to red, and then if you get red through green, you're up to yellow heat, and then if you get all of the spectrum, you're getting white heat, and then if you move beyond, then it starts to be dominated by the blue end of the spectrum, and you get that blue hot. They knew this, and it made sense that these curves would be here. What we're plotting is intensity on this vertical axis. We have frequencies getting bigger, that is wavelengths getting smaller along this axis, and the intensity, you may recall, is power per area. And there is also a principle that when you heat something up, the energy is equally divided among all of the wavelengths. That's called equipartition. And so if each of the wavelengths, that's a wavelength is sort of like area, and energy is sort of like power, that we would understand that if they're all getting equal amounts of energy and the wavelengths are getting smaller, then the intensity ought to be going up, and indeed it does. Until it stops going up and comes crashing down. And that was the ultraviolet catastrophe. How can we explain that? Why does it transition to ceasing to go up as the wavelengths continue to get smaller? And so the classic behavior would be that as the frequency goes up, that is, the wavelength gets smaller, the intensity goes through the roof. But what is actually observed is that for a while it does exactly what it's supposed to do, and then it deviates from that and comes crashing down. And what Max Planck proposed, not terribly seriously, was that if energy came in packages, quantum, and the size of the package depended on the wavelength or frequency, then the packages would get bigger and bigger for these higher and higher frequencies, and if everybody was getting an equal partition of energy, it could come to the point where the size of your package was so big that it was bigger than the amount of energy you got. And the nature of quantum is you've got to have an integer amount. You can't have a fraction. And so if you don't have a full integer amount, you get nothing. Again, suppose we have a situation where these are the wavelengths, these are the equal amounts of energy you get, and then if I take the energy and divide it by the wavelength, I get these intensities. And that would be this curve that goes off the map. But what Planck is proposing is that there are these energy comes in quantum, and that the size of the quantum gets bigger as the wavelength gets smaller. And so if everybody got 14, but the size of the quantum was 3, then you would only get 4 quantum. You couldn't get 4 2/3. And if the size of the quantum was 4, you would get 3, not 3 1/2. And if the size of the quantum was 6, you would only get 2, not 2 1/3. You don't get fractions of a quantum. And when the size of the quantum reached the size 15, you would get none. Then I take the number of quantums times the size of the quantum, and I get how much energy you got. And then if I take that energy and divide it by the wavelengths, I get the intensity. And that graph looks like that. And that is what we were seeing, and that was proposed as a possible explanation for this crashing down, this ultraviolet catastrophe. So the key idea is that energy comes in these packages, and the size of a package depends upon your frequency. This is a very small number called Planck's constant, and that frequency times Planck's constant gives you how big a quantum is for that frequency. Or we could replace frequency by the velocity divided by the wavelength. Okay. So Einstein took Planck's constant to explain another of the unresolved problems at the beginning of the 20th century, which was the photoelectric effect. And I expect you to know the photoelectric effect, that if you shine light onto a metal plate, it will knock electrons loose. And we can see that electrons have been knocked loose and that have reached this plate, even though it's negative and the electrons are negative, by detecting that a current is flowing. And we can vary the potential difference here, make this more and more lower and lower potential, until finally we make it so the electrons don't make it here anymore, that the electrons that are ejected are not energetic to make it here. That's called stopping energy, and so we can see the current go away. Well, in the photoelectric effect, it is the case that some colors of light will not knock electrons loose. And other colors, red for example, might not, whereas green and blue might be knocking electrons loose. And it turns out that the energy that these electrons have when they get knocked loose depends upon the color of the light. It does not depend upon how bright the light is. So you could send in blindingly bright red light, it wouldn't knock any electrons loose. You could send in very, very faint, so faint you couldn't even see it, blue light, and it would knock very energetic electrons loose. Green light would knock electrons loose, but they would have less energy. So, if this light is energy that is quantized, then it would be, as Planck proposed, that the amount of energy that a quantum would have would depend upon the frequency, and the blue end of the spectrum having or the ultraviolet end, indeed, having a higher frequency would have higher energy photons, energetic enough to knock an electron loose. And the electron goes away with any extra energy beyond what it took to knock it loose. So green, being photons or quantum with less energy, would have enough to knock an electron loose, but what was left over would be smaller. So it was easier to stop those electrons. And the red, each quantum did not have enough energy to knock an electron loose, and even if two red photons would make up enough energy to knock an electron loose, it wouldn't happen, because that superimposing, that adding of energies, is what waves does. And we're saying that light is not a wave, it is made up of quantum. And here is probably what I just said. Yes. So you can read that at your leisure if you like. Please do this problem. So here again, to try to illustrate what's going on with the photoelectric effect, I have an analogy. And instead of sending in light with various photons, we're going to throw money down from the balcony into the commons. I guess you call that the junior commons. Underclassmen will be down here, and if they get 45 cents, they get to get out of the commons. And if they don't, they have to stay. So if they catch a quarter, they can't get out. If they catch 2 quarters, they can't get out, because each photon is not energetic enough to get you out. And you can't superimpose, you can't add them together. The photons work by themselves. However, if you throw a 50-cent piece down, then the person who catches it does get ejected, and they leave with a nickel's worth of energy. That would be a green photon. If you send a blue photon in, that's like throwing $1 down. Very energetic photons, and the person who catches it gets out. That is sufficient energy to knock 2 people out, but that would be wave behavior. Here you have 1 quantum, and it is sufficient to knock 1 person out, and that person leaves with 55 cents worth of energy. So it's very different behavior than you get with waves. However, there's a problem. Waves do interfere, and they diffract, both of which having nodes. And you can't take a particle and add it to a particle and have it add to 0. That only works for waves. Waves can be transverse and thus polarized, but you can't have a transverse particle. That doesn't make sense. So there's a lot of phenomenon that seem to say that light is a wave. And there are also, like the photoelectric effect, phenomena that say that light is a particle. Light also has mass. It is bent by a gravitational field. So there is this terrible problem. Is light a wave or a particle? And the answer to that problem is not to say that it is both, not to say that it is one or the other, depending on how you observe it. No, the answer to that question is that light is a particle. But it is a particle with a non-deterministic path. And this adding to 0 was not an adding of quantum to quantum, but that non-deterministic path has probabilities of being in various places, And if you superimpose the probabilities, they can add up to a probability of 0. And that is what is going on with these locations, which are nodes. And this is what I just did. But this guy de Broglie said, whoa, wait a minute. If you're going to say that light can show both particle and wave behavior, is that also true with particles? And so he proposed that that's pronounced de Broglie, he pronounced that maybe particles had wave-like qualities, probabilistic qualities that he referred to as their wavelength, and he said it was equal to Planck's constant divided by their momentum. So here you have light diffracting through a hole, and it has to be a very small hole. You don't get diffraction unless the size of the hole corresponds with the size of the wavelength. But here are X-rays being sent through a metal crystal. You can't use a hole because it's too big, but the distance between atoms might be just right for the very small wavelength of X-rays. And here are electrons being sent through the same crystal. And I think there is no question that this looks like diffraction, and there are electrons behaving like waves. Of course, it is just a probabilistic phenomenon, but it is still useful to think about this thing called the de Broglie wavelength, and I will ask you to work with it. Here are two problems asking you to work with the de Broglie wavelength, assigning a wavelength to a baseball. Notice a wavelength that depends on how fast the baseball is going. The faster you make the baseball go, the smaller its wavelength would be. And I suppose if you sent a baseball at relativistic speeds, then it might very well have such a short wavelength that you could cause it to diffract. That would be a mean baseball to hit, that you would have this diffraction pattern that you would be swinging at instead of a particle. It is also, I think, very useful to understand energy levels in terms of de Broglie wavelength, that you could have an electron orbiting and having a wavelength that produced a standing wave, or you could have this other wavelength which produced a standing wave, but in between those two you would have wavelengths which didn't produce standing waves, and we understand that if you don't get a standing wave, you have nothing. So if you make an electron more energetic, its wavelength changes, and you get this other energy level. It's a very clever idea. So, history of our understanding of atoms. That we started with the realization that atoms were made up of positive and negative, and we thought, since the atoms overall are neutral, that what you had was this homogeneous mixture, referred to as the plum pudding model. And then comes the Rutherford atom, or the planetary atom, where Rutherford discovered that all of the positive and all of the mass were located at the center, with the electrons going around the outside, and very much like the planets go around the sun, you would have electrostatic force instead of gravity to hold it together. That was a very nice explanation of phenomenon. But there are a couple of problems. One of them is that an electron moving represents a current, and an electron moving in a curve represents a changing current, an accelerating electron, and accelerating electrons, changing currents, give off electromagnetic radiation. specifically, they create a magnetic field, but a changing magnetic field then produces a changing electric field. You have electromagnetic radiation. That is energy leaving the atom. And if the electron gives off energy, then it will have to go slower. And if it goes slower, it would move into a lower orbit. And it turns out it would take about a trillionth of a second for the electron to spiral into the nucleus. But they don't. How do we explain that? And so we have our third iteration of our understanding of the atom. This is called the Bohr atom, and Niels Bohr suggested that the reason they don't spiral into the nucleus is that they can only exist at certain energy levels, like at the previous slide, and that there is a lowest energy level called the ground state, and you can't go any lower than that because quantum doesn't allow it. It's kind of awkward, but it did a beautiful job of explaining spectral emissions, that you have these only certain energy levels are allowed, and in jumping between energy levels, the atom would give off specific frequencies because the energy E equals HF would correspond to a specific frequency, and so this was lovely, but it doesn't work. Okay, here's energy levels in the Bohr model of the atom. And the problem it doesn't work is because it has a point-like object with a well-defined location moving along a well-defined trajectory. And something called the Heisenberg uncertainty principle, which we will learn about in the next lecture, says no. You cannot have a well-defined location and a well-defined trajectory, well-defined motion simultaneously. And so ultimately we have moved to what is called the quantum model of the atom, where we no longer pretend like they are going in well-defined paths or that we know exactly where they are. There's a probability that it is someplace in here and moving in that location, but I no longer pretend to know what it is doing or where it is. And so you have the quantum model. This model, however, is still useful for understanding this spectral emission. That one of the things I would expect you to get is that if I give you an atom with 4 energy levels, then you ought to be able to count all the radiations that could be given off. It could jump down from the highest energy level. It could jump 3 energy levels down, or 2 energy levels, or 1. Each one of those would correspond to a different amount of energy, and so a different frequency given off by the atom, and that would correspond to a different band of color here. And then from the penultimate energy level, it could jump all the way down, or 1 down, so that's 2 more frequencies, and then from this it could jump down just 1 to the ground state. And so there would be 6 spectral lines. They might not all be in the visible part of the spectrum, but I would expect you to be able to count up to 6 there. Okay. This also does a very nice job of explaining some other phenomenon known as phosphorescence and fluorescence. That phosphorescence is when you take in energy and then re-radiate it, but you do it at the same frequency. But you don't re-radiate it right away. This delay that you would feed energy in, and it has to be the right amount of energy to correspond to a difference between energy levels. And if you feed that energy, then the electron will jump. We say it absorbs the energy, and instead of re-radiating it right away, which is scattering, it spends a little bit of time here before it jumps back down. And so you have glow-in-the-dark frisbees, where you put it in a bright light, and then over a long period of time, it re-radiates that energy. Fluorescence is, instead of the energy jumping right back down at the same amount of energy, hence the same frequency, it might jump down in 2 steps. And so you would feed energy in at one frequency, high energy, usually ultraviolet. And it jumps way up here, and then it jumps back down in 2 smaller steps. And so the frequency given off is different than the frequency was put in. That with fluorescent lighting, we put energy in ultraviolet radiation by exciting mercury gas inside. And then it hits the fluorescing material, which coats those tubes of mercury gas, and they take in the ultraviolet, but they re-radiate light that is in the visible part of the spectrum. And so you have fluorescence. The other phenomenon that is nicely explained by this Bohr model of the atom is the behavior of a laser. With a laser, you feed the energy in, and again you have this phosphorescent quality that it doesn't jump back down, but this time it doesn't make up its own mind when to jump back down, but instead it jumps back down when some light passing by stimulates it to jump back down. And when it jumps back down, so you fed energy in, we caused the gas to be energized, then we send energy through. This energy is not causing it to jump up. This is other energy that causes it to jump down, and you have that energy that triggered it to jump, plus the energy given off by the jumping back down. That the acronym LASER stands for light amplification by stimulated emission of radiation. So this stimulating the emission is very important. Now, as far as this amplification goes, that is this amplification because these two are in phase. We say they are coherent. Because it jumps back down when it is stimulated to, the light that is given off due to the stimulation is exactly in phase with the other light. And when you can get 2 beams that are coherent, it is possible to get them to stay very close to one another. If 2 beams are incoherent, not in the same phase, there is a limit to how tightly you can bundle them. They seem to knock into one another and knock one another apart. But when they are in phase, they can march right close to one another and stay together. And so that is where the amplification comes from. That is where you take this light and put it in a very small area. It becomes very intensified, and you can use it to burn through steel or do operations, the laser. Okay, and that is the end of the first day's lecture.